Okay, so last Thursday we studied pressure. So first we studied there are different pressure units. The first one is the SI unit, Pascal, which is Newton per meter square. So force divided by area is pressure. However, this 1 Pascal is just too small, so we use kilopascal. 1 kilopascal is 100 Pascal. Then how big 1 kilopascal is? The atmospheric pressure, 1 atm, is the pressure at the sea level, and which is 101.325 kilopascal. So we know two units. One is Pascal and the other one is atm. There's one more pressure unit, which is bar. 1 bar is 100 kilopascal. Sometimes you see atmosphere, bar, or kilopascal. So these are how you convert between different units. Okay. Then how pressure changes? Pressure only changes in the gravity direction, and the change in pressure can be determined by delta P. This delta means difference in pressure can be determined by density rho times gravity G times H, height. So this is the only equation we are going to use in this chapter. Okay. So what does it mean? Pressure changes with respect to this gravity and density. So the higher the density, the greater changes in pressure, and also H, the height. And there's a very interesting figure that you want to see here, which is this one. So this is water, and there are many points A, B, C, D, E, F, G. If you compare the pressure value at point A and the pressure value at point B, they are the same because they are at the same height from the surface. If you look at this surface, you see this upside down triangle. This means the pressure on this surface is the atmospheric pressure. So if you see this one upside down triangle, you can say this one is 1 atm. Then if I say the pressure at this interface between water and air is 1 atm, what does it mean? It means on this surface there is atmospheric pressure acting on the surface in this way. And what is the pressure value of this atmosphere? 1 atm. So 101.325 kilopascal. Is this the only pressure acting on this interface? No. What about if this atmospheric pressure is the only pressure acting on this inner face, then this inner face should move downward because there's a pressure acting on in this direction. So, but when you see water, you see this water surface remains constant, right? It doesn't go up and down. That means there is a pressure by water acting on this inner face, and that is also 101.325 kilopascal. Because the pressure by the air and the pressure by the water, they are the same. That's why this inner face doesn't move up or down. What about the atmospheric pressure? This green is greater than the water pressure. Then this inner face is going to move downward until you have a pressure equilibrium, which means that air pressure and water pressure are the same. What about water pressure is greater than the air pressure? This water level is going to move upward until you have a pressure equilibrium. So when you see water level is, stay at a certain point, that means that, the pressure by the fluid on top of it and the pressure by the fluid at the bottom, they are the same. Only that point, you have this interface stays at one position, okay? So if you see this upside down triangle, you can see, the atmospheric pressure acting on the surface is 101.325, as well as the water pressure acting on the surface is also the same amount of pressure. Then what is the pressure value at this point A? Can you determine that? Yes. By how? By using this equation. The difference in pressure is rho GH. So we know the pressure at this inner face because we see this upside down triangle. So the pressure at this point is going to be 1 atm. So pressure at this point, let's say P1 is 1 atm. Or we can say 101.325. They are the same thing. Then what about pressure at point A? I'm going to say this is P2. Then we can use this delta P rho GH. Then let's see how we can use delta G rho GH. Between these 2 points, delta P should be the same as density times gravity times H. Then how can you determine this delta P? P1 minus P2 or P2 minus P1? Delta is the difference. Can this difference be a negative value? No, this should be a positive value. Then between P1 and P2, which one is greater than the other? P2. So if you want to determine this delta P, is it P1 minus P2 or P2 minus P1? Yes, P2 minus P1. Then this delta P is P2 minus P1. It's not P1 minus P2. Is density rho. Density rho of what? Whatever the fluid between P1 and P2, that is water. So density of water times gravity, 9.8, and H, this H, the height between these 2 points. Then what is P1? Oh, that is 101.325 0.325 kilopascal. What is the density of water? We studied that when we studied specific gravity, right? 1,000 kilogram per cubic meters. What about gravity? What is gravity? It depends on location. Yeah, depends on whether we are on the Earth or on the Moon or Mars. But 9.8, right? Meter per second square. And height h. Let's say just 10 meters. Minus. So if you solve this equation, you get P2. Okay? So what about if this is the swimming pool in the SAC, the Student Activity Center? Then H may not be 10 meters, just like about 2 meters. Okay? Then let's calculate the pressure at the bottom of the swimming pool in the SAC. We can do that by using this one equation. So let's calculate that. 9.8 times 1,000. This is going to be 9,800 kilogram per cubic meters times meter per second square times, oh, there are two, I forgot about that. 19,600 kilogram per cubic meters times meter per second square times meter, right? So this unit, and this unit should be 101.325 kilopascal minus P2. So can you determine P2? So what about this unit? Kilogram per cubic meters, and we have a meter, so you can cross them out. So it's going to be kilogram per meter second square. So we have 19,600 plus 101.325. So the pressure at the bottom of the swimming pool is going to be 1900, 701.325 kilopascal. Is it correct or wrong? Why it is wrong? Because we haven't checked the unit, right? Then how do you check the units? Because this one is Pascal, this one is kilogram per meter second square. How can I compare these two? Did we study that? Yes, we did. If you remember primary dimensions and secondary dimensions. So secondary dimensions, a secondary dimension is a combination of primary dimensions. So if you have a secondary dimension, you can divide into 2 or 3 primary dimensions. By doing so, you can check dimensional homogeneity. Whenever you have an equation with all different units, you need to check dimensional homogeneity. So let's do that. Then you just need to remember one thing. What are the primary dimensions in thermodynamics? Of course, you know that there are many primary dimensions, but in thermodynamics, there are only 4 of them. What they are? Primary dimensions: length, meter; mass, kilogram; time, second; temperature, Kelvin. So let's see. If you look at the units on the right-hand side, we have a kilogram, mass; meter, length; and second, time. So the right-hand side of this equation only has primary dimensions. No problem. What about the left-hand side? We have a Pascal. Pascal is none of these, so it is a secondary dimension. So let's convert this secondary dimension into a combination of primary dimensions. So let's do that. So we have this one on the left-hand side. Let's look at this Pascal. Pascal is a unit of pressure. Pressure is force divided by area. So Pascal, pressure is force divided by area. What is force? Newton divided by area, meter square. So Pascal is Newton per meter square. Newton per meter square. Now, are they primary dimensions? Not yet. Meter is a primary dimension, but Newton is not. What is Newton? The unit of force. So force is what? Mass times acceleration. Force is mass times acceleration. What is mass? Kilogram. Acceleration. Meter per second square. Meter per second square. And we have meter square at the bottom. So I'm going to say meter square. So what do we have? Kilogram, meter, second square, meter square. And we have a meter in the numerator and meter square in the denominator. So what do we do? So the unit on the left-hand side is kilogram per meter times second square. Now, let's check dimensional homogeneity. This unit looks exactly the same as this unit. So the unit on the right-hand side is what? Pascal. However, we have a kilo in front. So this equation is incorrect because the right-hand side is Pascal, the left-hand side is kilopascal. So you want to use kilopascal only or Pascal only. Okay? Then this equation becomes E2 minus 101.325 kilopascal, and the right-hand side, this one is Pascal, so let's use kilopascal. How do you do that? Divide this number by 1,000. So it's going to be 19.6 kilopascal. Then what is P2? P2 is 120.3925 kilopascal. This one looks much more reasonable compared to this one. If you're in this pressure, what you're gonna be? Cannot survive, right? So that's how you determine the pressure at a certain point. Okay. In this case, the pressure at point A, assuming the height is 2 meters. Any question? So from this, you can see P2 is greater than P1. The P1 was only 101, and P2 is, oh, I'm sorry, there's one. P2 is this one, 120. So pressure goes up in this direction, gravity direction. Then if you go back to this figure again, now let's look at the left-hand side. You see this one, this arrow. The length of each arrow indicates the pressure. So near the surface, the pressure was only this much, which is 101.325 kilopascal. But when you go deep, pressure goes up, right? And you can see longer arrows, longer and longer and longer. And at the bottom, you have the longest arrow that shows the pressure at the bottom is going to be the highest, much higher than the pressure at the top. So usually pressure distribution looks like this. It goes up in the gravity direction. This one is gravity direction, right? The same thing. If you look at this figure, you can see the pressure goes up in the gravity direction, but pressure does not change. The length of arrow does not change in this horizontal direction, right? The pressure only changes in the gravity direction. Then now, let's look at this point A. We just determined the pressure value at this point A by using this equation. Delta P is rho GH. Then what about the pressure at point B? What is the difference between point A and point B in terms of pressure? They are the same because they have the same gravity, same H, and same density, water. So delta P, the difference in pressure between A and the surface, B and the surface, they are the same. So the pressure values at A, B, C, D, E, F, G, they are all the same. Okay? From here, you can see when you have 2 points at the same height within the same fluid, pressure values are the same. And what about here? There are 2 more points, H and I. What is the, when you compare the pressure values at H and pressure value at I, are they the same because they are at the same height? Not anymore because there's a mercury. Mercury is heavier than water, which means the density of mercury is greater than the density of water. So pressure changes is more significant compared to pressure change in water. Then between P, pressure at H, pH, and pressure at I, PI, which one is greater than the other? pH and PI. Should be H because mercury is heavier than water. So pressure increase from this point to the bottom. From this point to the bottom, this one is greater than the other. And how heavy mercury is? What is the specific gravity of mercury? Specific gravity of mercury is 13.6. Then can you determine the density value when you know this specific gravity? Yes, you can, because specific gravity, Sg, is the density of this one, mercury, Hg, divided by the density of standard substance, which is water at 4 degrees Celsius. This one is 1,000 kilogram per cubic meters. Specific gravity is what? 13.6. So what is the density of mercury? 13,600 kilogram per cubic meters. Okay? So we learned 2 things. Pressure increases in the gravity direction. And by how much? By delta P rho GH. Pressure changes by that much if you move in the gravity direction. Any question about this slide? Yes. This one? 120.925. Delta P is 19.6 based on delta P rho GH. Then before going to the next slide, let's review one more thing. We, at the beginning of the pressure, we studied there are absolute pressure and gauge pressure, and there is atmospheric pressure. So if you think about a chamber which is pressurized, and there is a pressure gauge. If this pressure gauge shows it's about 200 kilopascal, and the outside pressure is atmospheric pressure, PATM is 100 kilopascal approximately, then what is the pressure inside the chamber? 200? No, because this 200 is what? Gauge pressure. This 100 is what? Atmospheric pressure. And absolute pressure is gauge pressure plus atmospheric pressure. So the pressure inside the chamber, the absolute pressure is going to be 300 kilopascal. That's what we studied last week. Then how can we measure this gauge pressure? By manometer. And how can we measure this atmospheric pressure? By a barometer. So we are going to study how these two work. Okay, so starting with manometer. Let's talk about manometer first. A typical manometer looks like this one. We have a gas tank whose pressure is unknown, and we have this manometer, usually looks like a U-shaped tube, and the other end is open to the atmosphere. And if you know the density of this fluid, so there are two fluids, one is this unknown gas, and this is the interface between this unknown gas and a known fluid. What kind of fluid do we use in general? Mercury. Why is that? Because of this mercury density is pretty high. So you can change the pressure by a small amount of mercury. We will talk about that later when we study barometer. So let's assume that we have a mercury here. Mercury is Hg. We know the density of mercury, right? The density of mercury. The specific gravity of mercury is 13.6 multiplied by 1,000 kilogram per cubic meters. Mercury density is going to be 13,600. Then we need to know the H, the height. Let's assume that maybe 1 meters. Okay. Then you can determine the pressure of this unknown gas. The first thing you need to do is that you need to look at you need to find the starting point. What is the starting point? The point whose pressure is known. What pressure is known in this, the diagram? Do you know any pressure at any point? Yes, we do. Which one is that? Do we know the pressure of this gas? Do we know pressure of this mercury? It depends on the location, right? And what location? this one. At this surface. This surface is open to the atmosphere. What does it mean? Do we assume that this surface goes up or goes down? No. We assume that it is stationary. It doesn't move. Then what is the pressure value at this point? The atmospheric pressure. So we should have upside down triangle here to show that this one is at the atmospheric pressure. What is the atmospheric pressure? Oh, we don't know. So let's assume it's going to be 100 kilopascal. It's our assumption. Assume PATN, not the automatic teller machine, is 100 kilopascal. Then, what do we need to do? We need to find an interface between two fluids. In this case, we have a gas, we have a mercury. The interface is here. This one, number 1. So we have number 1 here. So I'm going to say the pressure at point 1 is P1. And at the same level, there is a number 2. So I'm going to say this one is, the pressure at this point is P2. Of course, we have pretty much no idea about, the point number 2. It's just at the same level as this P1. We know point 1 is the interface between this unknown gas and the mercury. But P2, it is just at the same level, same height between 1 and 2. Then, what is the relation between P1 and P2? Is P1 greater than P2 or P2 greater than P1? Or are they the same? They should be the same because if you remember this one, what is the pressure at A? What is the pressure at B, C, D, F, G? They are the same as long as they are at the same level within the same fluid. Now, if you go back here, P1 and P2, they are at the same level and within the same fluid, mercury. So P1 should be the same as P2. Am I right? Yes. Then, do you know, the either P1 or P2? We do not know their pressures. However, we can calculate one of them. Which one? P2. Because we know PATN by using delta P rho GH. Now we are going to use the only equation we know in terms of pressure, that is delta P is rho G and H. So let's use this equation to determine P2. First, delta P. Delta P is the difference in pressure. So we can look at the difference in pressure between number 2 and atmosphere. So it's a PATM and P2. This delta P, is it PATM minus P2 or P2 minus PATM? It should be P2 minus PATM because P2 is greater than PATM because we know density and pressure increases in the gravity direction, right? So this P, the delta P, difference in pressure is going to be P2 minus PATM is, you cannot say PATM minus P2 because P2 minus PATM is a positive value because we know P2 is greater than PATM. P18 minus P2 is going to be a negative value. The difference in pure pressure cannot be a negative value, right? Then what kind of density is that? Density of the fluid between this point and this point. What kind of fluid is here? Mercury. So we have the density of mercury times gravity times H. So if you know the atmospheric pressure, then you can determine P2. Now, from this one, P1 and P2 are the same because the point 1 and point 2 are at the same level within the same fluid, mercury. So from this equation, we learned P2 is, if you move this one to the right-hand side, P18 plus the density of mercury gravity times H. Now we know P1 is the same as P2, so we can say P1. Then P1 is the pressure of what? Mercury and gas. So when we say the gas pressure in the chamber is going to be what? Technically, let's assume that this P1 is about approximately, let's say, 120 kilopascal. Let's assume that, that after when you calculate this one, you got P1 is approximately 120. Let's assume that. Then what is the pressure somewhere, in the middle of this chamber? Let's say here, P3. Is P3 greater than P1 or P1 is greater than P3? Technically, P1 is greater than P3 because the gravity increases and the pressure increases in the gravity direction. However, what is the pressure variation of the gas? This one. When we talk about pressure change in this mercury, it is significant because the density of mercury is what? 13,600 kilogram per cubic meters. Then what is the density of most gases? What is the the most common gases that we study? Air. What is the air density? What is the air density? We cannot say that because air density changes depending on pressure and temperature. But what about this room temperature and atmospheric pressure? Approximately 1.2 or 1.3 compared to 13,600. The density of air, the density of gas is almost nothing. So in general, in thermodynamics, we assume that gas pressure does not change, even though technically the pressure at the bottom should be greater than pressure at the top. But the approximately here is going to be 120, here is going to be 119.9999 something. So practically, we can say gas pressure does not change, unless you compare gas pressure, air pressure difference between Mount Pleasant and on top of Mountain Everest. Then it's a significant. But if you look at this gas tank, do you expect that the gas tank size is like Mountain Everest? No. Then what is the pressure difference? Small. When you go to the second floor of this building, is the second floor? This is the first floor. Technically, pressure goes down. So when you go up, do you need an oxygen tank to breathe? No, because even though there is a slight pressure change, we cannot feel that. It's very small. What about if you go to What is the tallest building on campus? What? What is the towers? Oh, okay. I've never been there. Okay, yeah. So if you go to the, the top floor in there, is top floor penthouse? No. I was just, so if you go to the eighth floor, you need an oxygen tank? No, because the pressure change is negligible, unless you climb up the Mountain Everest. Even these days, the people climb Mountain Everest without oxygen tank, even though there's a pressure decrease. So when we say gas pressure, not liquid, gas pressure, we assume that it is constant. So when we say the gas pressure is, when we look at the interface between this gas and this liquid, if you determine the pressure at this interface, we assume that the pressure here is the same as pressure anywhere in this gas chamber. So the gas pressure is going to be what? P1, that is P of the gas. So you can determine this pressure by the gas. If you know the value of atmospheric pressure, you can calculate this gas pressure if you know the atmospheric pressure. Because this one we know 13,600. This one we know 9.8. This one, if you assume that it's 1 meter, then you can calculate this part. However, we still need the atmospheric pressure to determine the absolute pressure of this gas. That's why we have gauge pressure. That's why we have a gauge pressure, because you cannot determine this absolute pressure by this manometer. Because according to this manometer equation, you need to know the atmospheric pressure. If you do not know the atmospheric pressure, the only pressure you can calculate is going to be gauge pressure. Then if you know atmospheric pressure, then you get the absolute pressure. Okay? Any question about this manometer? We have a example. We have an example problem at the end of this chapter. So we are going to, solve a problem, related to this weird-looking manometer. I don't know if you design manometer like that, you need to find a new job, right? But we just made it complicated, so you can practice the pressure changes in this manometer. So that's how manometer works. Then what's the next one? So we learned, how manometer works. Usually has a U-shaped manometer, and it is filled with a fluid, usually liquid, with a known density value. So you can calculate gauge pressure. Then let's talk about barometer. Then how can we determine this atmospheric pressure? We can calculate this, we can determine this gauge pressure by using this manometer. We just did, right? If you know atmospheric pressure, you can calculate, the gas pressure. What about barometer? It's pretty simple. This is barometer. And you can make your own barometer today and measure the atmospheric pressure tonight. You can do that. You just need a tank and this one, a tube. That's all. And you also need to, to measure the length of, so like a ruler, okay? So that's all you need. So let's see how this manometer works. Barometer. It's pretty simple. First of all, let's use water. You prepare a water tank and filled with water. course, it's a water tank. So you're going to fill this with water, about this much. Now you are going to, prepare this tube and position the tube at the beginning like this. So you can completely fill this tube with water. And then now you are going to rotate this one this way. So initially, everywhere in the tube is going to be filled with water. Then let's see what's going to happen. Then if you move this tube upward, then you will see, if you move this, the tube upward, then you will see this is the water tank, and you have a tube like this, and water is going to move down and stop somewhere. And this is what happens. I need to move this water down up to this much so I can explain. Then this is the water tank, and this is the tube, and you fill the water about this much. Then let's see what happens. Is there any pressure, anywhere in this parameter? Yes, where? This one? Yes, because this surface is open to the atmosphere. So what is the pressure at this point? I'm going to say upside down triangle. The pressure at this interface between atmosphere and water is going to be the atmospheric pressure. Why is that? Suppose there's a pressure acting on this surface by the air, and there's a pressure acting on this surface by the water. So let's say that this one is water, this one is air. So if I say, what is the relation between pressure by air and pressure by water on this interface? Which one is greater than the other? The water pressure higher or air pressure higher? Yes. What about if air pressure is greater than water pressure? It goes down. So it's going to move down and pushing this water upward. What about water pressure greater than air pressure? It goes up and then this water comes down, right? When you see it, so initially it's going to move up and down, and then it stops somewhere. And once you see the surface is, the interface is not moving up and down, then you can measure the atmospheric pressure. So when this interface doesn't go up and down, the pressure by air is going to be PATM. The pressure by water is also PATM. So this interface is going to be atmospheric pressure. Then, what about, the right here? I'm going to make an imaginary surface about here. I'm going to say this one is P1. What is the relation between P1 and atmospheric pressure? P1 greater than PATM or PATM greater than P1? Are they the same? Yes, they are the same because we learned from here P1, PB, PA, PB, PC, PD, PE, PF, PG, they are all the same because they are at the same level and they are within the same fluid. The same thing. Within the same water and same level, so P1, PATM, they are the same. So this one is PATM. P1 is PATM. Then, now this is a tricky question. What is the pressure at this point? At this interface? Is it interface? What is the pressure on this surface? greater than atmospheric pressure because it is up and the gravity direction is downward. So pressure goes up when in the gravity direction, but this one is the opposite direction. So pressure cannot be greater than atmospheric pressure. Then what is the pressure value here? This pressure is the same as this one, which doesn't make sense because delta P is rho GH. According to that equation, the pressure at this point should be less than this one. So what is the pressure value at this one? Lower. Yes, but how much lower? We can find the pressure value here. What is the pressure value here? Think about the definition of pressure. No. What is the definition of pressure? What is pressure? Force by, oh right, mathematically. Yeah, in physics, you're correct. In physics, what is the pressure? Pressure is the force by fluid, right? Fluid is the one, the making pressure. So, what kind of, the fluid is acting on this interface? Yes, water. And what is it? So, initially, I fill this tube with water and then rotate this tube to look like that. So initially, water was completely filled up to here, and then it moved down slowly and stopped here. So what is the fluid in here? Oh. Theoretically, yes, but in practically, it is. What else other than water? So somebody made a hole here, and fill this one with air. Now, then what's inside? If there is no water here, yeah, water vapor can be very small amount, but you can neglect that. So what is here? Yes, vacuum. What is the pressure by vacuum? What is the definition of pressure? Force by fluid. Then what is the pressure value by vacuum? Zero. So the pressure at this point is going to be zero, practically. Yeah, water vapor is possible, but very small amount, unless you increase temperature or decrease pressure. So at the typical atmospheric pressure, we can neglect the effect of water vapor. So pressure at this interface is going to be zero. Then what is the pressure by water at this interface? Zero. Even though there is water pressure, it will move up and down until it becomes zero because there's nothing here. So at this point, pressure is zero. Now, do you remember one equation that we studied here? Delta P, rho GH. Can you apply that here? Yes, we can. So the only thing we need to know is, since the equation is delta P is rho GH. So what we need to know, H. So if you can measure this H, clear. So this one is H. If you can measure this H, you can determine, you can solve this delta P rho GH. What is delta P? Between P ATN and T0, which one is greater than the other? It's a very silly question, right? Of course, this one is greater than zero because pressure cannot be a negative value. The delta P is PATN minus zero, so it is PATN. PATN is what? Density of what? Air? No. Water. Gravity times H. So if you know the density, if you know the gravity, if you know the H, then you can measure the atmospheric pressure. So if you make a barometer at home, what should be the H value? You can calculate that, assuming that the atmospheric pressure is near the sea level. So let's say it is 101.325 kilopascal, and which is the density of water. You can assume that 1,000 kilogram per cubic meters. What is the gravity? 9.8 meter per second square. What is H? So now you can calculate that. I'm going to calculate that. 101.325, but be careful, there's a kilo. Okay? And you remember we did dimensional homogeneity. If you multiply kilogram per cubic meters, meter per second square, and meter, it becomes Pascal, not kilopascal. So when you do the calculation, you need to multiply by 1,000, right? Or divide the right-hand side by 1,000. So 101.325 divided by 1,000, then divided by 9.8. So it's going to be about approximately 10 meters. So if you make this device, barometer, in your house, you need to install it in your backyard because it's 10 meters. So now you're an engineer. Are you going to make it or are you going to improve it? You don't want to make a barometer like 10 meters. Then what is the simple solution to that? If you look at this one, what is the simplest way to miniaturize the system? Yes, you can use a mercury because density, 1,000, too small. Let's use heavier fluid. What is the heaviest fluid? Mercury. So it's going to be 13,600. Now I'm going to change this one with what mercury? Hg. No water. Then what is the this value? I'm going to recalculate that. 101.325 divided by 13,600. Now divided by 9.8. 0.76 meters, about 70 centimeters. Now it looks reasonable. Okay. 0.76 meters, about 76 centimeters. 1 inch is 2.54 centimeters, so you can get the idea. Approximately about this much. Now, let's go to our weather channel. Let's see, what kind of pressure unit they use. So I'm going to search for weather in Mount Pleasant, Michigan. Oh, you cannot see this one? Oh. Weather in Mount Pleasant, Michigan. I prefer this weather.com. So I'm going to see it's a 64 degrees Fahrenheit, so it's nice to walk outside, right? So if you go down, or no, I want to see what happens in today. So I need to click this one, right? Today. So what is the atmospheric pressure? Can you read it? What is the atmospheric pressure? 30.38 inches. Is it Pascal, ATM, bar? And what is this unit? Inches. So what does it mean? Yes. So they have a barometer, and I measured the height. It is 13.38 inches. if they have a mechanical engineer, they can convert it into a, the pressure unit rather than add, right? So that's where you can, define this one. And once you get this value, you can convert this one into what? Kilopascal. So 30.38 inches. That's the reading from the barometer. So let's do that. 13.38 inches. And this is English unit. In this thermodynamics in classroom, we are going to use SI unit. So what is that 30.38 inches in meter? So just for your information, 1 inch is 2.54 centimeters. In other words, 0.0254 meters. So if you convert, it's going to be 77.1652 centimeters, which is 0.771654 meter, which is slightly greater than 0.76. So you can say the atmospheric pressure is pretty high, a little higher than the usual. So when atmospheric pressure is a little higher than usual, is there going to be a raining or sunny day? Yeah, usually when pressure goes up, it's going to be sunny day. When pressure goes down, then there will be possible rain and etc. So it's going to be a sunny day today. So that's how barometer works. Any question? So that completes chapter 1. Now we have a couple of practice problems. So let's solve them together. And that will be all for today. We have 8 minutes. That's plenty of time. So let's do that. Water in a tank is pressurized by air, and the pressure is measured by a multi-fluid manometer. Don't make multi-fluid manometer. The single fluid is fine, right? And as shown in the figure, determine the gauge pressure. So always check whether do I need to determine either gauge pressure or absolute pressure. So this one is gauge pressure. When you hear gauge pressure, you need to write down this equation. Absolute pressure is gauge pressure plus atmospheric pressure. And H1, H2, H3 are available. Take the density values of each of them is also available. So we have everything. So let's solve this problem. Of course, I wrote this equation. Whenever you see a manometer, forget about this equation and always stick to 1. You can assume that everything is an absolute pressure, everything is gauge pressure. Either way, just don't mix gauge pressure and absolute pressure. Okay? So let's solve this equation. Which one do you want? The absolute pressure or gauge pressure? It's very simple. If you only use gauge pressure, you assume that atmospheric pressure is 0. If you use, the absolute pressure, you can assume that atmospheric pressure is 100 kilopascal or something, and subtract that value later, okay, to determine gauge pressure. So we can try absolute pressure. So if you, use absolute pressure, that means you need to assume atmospheric pressure. For simplicity, I'm going to assume the atmospheric pressure is 100 kilopascal. Okay. So where is it? This one. There's an upside down triangle. This is where the fluid is open to atmosphere. So I'm going to say at this location, pressure is going to be 100 kilopascal. So now we need to name each, the interface. First, I'm going to say this point is number 1. This point is number 2. This point is number 3. This point is number 4. This point is number 5. And this point is number 6. And here is number 7. Okay? So, since we know the atmospheric pressure, we are starting from number 1 and use delta P rho g H to determine number 2 and number 3 and number 4. Why there's number 4 here? Oh, my bad. Number 4 should be here. Oh, what am I doing? The number 4 and number 5 and number 6, number 7. Okay. So let's determine number 2 first. P2. If you want to determine P2, we can apply delta P rho g H. So I'm going to use the delta P is rho g H. What kind of delta P? Between P1 and P2. We know P2 is greater than P1, right? So delta P should be P2 minus P1. So this one is P2 minus P1 is density of what? Mercury. Hg times gravity times H of what? H3. And from this equation, we know P1 is 100 kilopascal. Then, now let's look at, the P2 and P3. What is the relation between P2 and P3? Yeah, they're equal. So P2 is P3. Now, 3 and 4. Can you apply delta P rho g H between 3 and 4? Yes, you can. 3 is in oil and 4 is in oil, and we can use this H2 to determine P4. So between 3 and 4, we can apply delta P rho g H. Between 3 and 4, 3 is greater than 4, so P3 minus P4 is density of what? Oil times gravity times H2. By the way, P3 should be from here. Now, let's rewrite this equation in terms of P4. P4 is P3 minus density of oil times gravity times H2. In this case, P3 is P1 plus this one, P1 plus density of mercury times gravity times H3. So P4 is P1 plus density of mercury times gravity times H3 minus density of oil times gravity H2. Now, between 4 and 5, what is the relation between 4 and 5? They're equal. So P4 is P5. Now, 5 and 6, they are in the same fluid, water, at the same elevation. So this one is the same as P6. So we got P6. Now P7. We can apply delta P rho g H between 6 and 7. So let's do that. Delta P is rho g H. Now I'm going to use it between 6 and 7. We know 6 is greater than 7. So this one is P6 minus P7 is what? This one. P1 plus density of mercury times, what am I doing? P6 minus P7 is rho GH, density of water, times gravity times H, H1. And from this, we know P6 is this one, goes in here. Then let's rewrite this equation in terms of P7. It's going to be P1 plus density of mercury, gravity H3 minus density of oil times gravity H2 minus density of water times gravity times H1. And this P1 is 100 kilopascal, so you can determine P7. From this equation, mercury density is 13,600, gravity 9.8, H3 is 0.46, density of oil 850, gravity 9.8, H2 is 0.3, density of water 1,000, gravity 9.8, H is 0.2. Then you can determine P7. If you do, the answer for this P7 is going to be 156.9 kilopascal. So that's the answer. Am I right or wrong? If I say like that, you suspect that this might be incorrect, right? So this is incorrect. What is the problem here? There's no calculation mistake. What mistake I made? Right, it has to be a gauge pressure. Now you need to subtract this one back. Minus 100 kilopascal, then you get 56.9 kilopascal in gauge. Okay. So again, when you use this equation, you can assume the atmospheric pressure and solve all of them. And since you need to determine the gauge pressure, now you need to subtract the atmospheric pressure that you assumed, right? Any question? No. Then this Thursday we are going to solve this solve this problem. That will be all for chapter 1, and you can start solving your first homework. All right. Thank you. See you on Thursday.